So here we are beginning Unit 5, which is Mathematics and Chemistry, and we've already done a lot of this already in the gas law unit, where we took the history and development of the gas laws and the development of the atom based on Dalton's work, Avogadro's work, Gay-Lussac. We did a law of combining volumes. We've done the mole concept. So we've done a lot of work here already. And we've already done formula or molecular mass. So they basically are synonyms. Formula mass is the grams per mole for something that is ionic, because all you have is a formula, and that formula because you have the lowest ratio of ions in a crystal. Whereas a molecular mass, you have molecules, and these are things that have definite shape and definite number, whereas an ionic compound makes these crystal lattices that are in 3 dimension from the ions. So you also hear gram formula mass, gram molecular mass, and if it's an atom, okay, you'll hear the word gram atomic mass. Any case, that being all said, let's get to the bottom of it. Basic mole theory states that if I compare two volumes of two different gases under the same conditions of temperature and pressure, I'll have the same number of molecules, particles. And what we talked about early in the year is seats. There's only a certain number of positions that gases can take place. And we don't really care about how many positions. We really care about them being the same. So by comparing equal volumes of gases, we learned we compared really the individual particles. And if they were atoms, we were able to come up with the relative atomic mass of them. So when we looked at hydrogen, a box of hydrogen, a box of oxygen atoms, we came to the conclusion that if they followed Avogadro's hypothesis, very simply, that this box, or the hydrogen box, was 1 gram, or I'm sorry, had a 1 to 16 ratio. And that 1 to 16 ratio, okay, was held true no matter what size containers we use, as long as the conditions of temperature and pressure were the same for each, and each had the same what? Volume, then they had the equal number of particles. Now, this 1 to 16 ratio was nice, but we had to do some math to get to it. So we picked a volume that gave me exactly a 1 to 16 ratio in grams, and that volume was 22.4 liters. So we considered this to be a universal container because it gave us the ratio in grams. So we knew the mass, or the relative atomic mass of hydrogen was 1. We knew the relative atomic mass of oxygen was 16. It was 16 times more massive than the hydrogen. What we did is we picked this container, okay, 22.4 liters. You picked this container because it gave us this ratio in grams that matched the atomic mass for each atom. So if I had Na2S in each seat, what I really have is 2 moles of sodium. So if I had pure sodium in here, it would be 23 grams. But if I've got 2 sodiums per each one of these places that atoms can exist in this box, it'd be twice as much, 46. And if I put a sulfur into the same seat, you'd be adding the mass of sulfur. So if you've got if you have sodium sulfide, which is 2 sodiums per 1 sulfur, what that tells us is that we really have 3 moles of atoms in this container at STP if this was a gas. So if I've got a mole of this, I've got 2 moles of sodium, right? In 1 mole of this compound, you've got 2 Na particles and 1 S. So when you count the individual relative atomic masses, we'll come up with the mass per 1 mole of that particle. In any case, we went through this exclusively. I love to make sure that you understand mole concept as opposed to just doing problems. But let's get to the problems. They're not so hard. Okay, so I want to find the mass per 1 mole. I want that. The reason I want that, I want a converting factor if I have moles or grams and I want to go back and forth. This is probably fundamentally the most important thing we do in chemistry, is able to mass out something as small as an atom and know how many atoms we have just by using mass. We can't count these small particles, but as long as we have a converting factor that goes from how many grams per a number, we can do that. So how do we come up with that converting factor? Very simple. We know that we have 2 sodiums in our compound. And we're going to find this per 1 mole. So if I got a mole of this, which is some number, it's Avogadro's number, but we'll call it some number, then I have 2 moles of sodium atoms. And each mole of sodium atom is 23 grams. I'm getting that from the periodic table. If you look at the periodic table, sodium is 23. That's its mass, atomic number 11. That's where I'm getting it. And of course, that gives me 46 grams. Now, there's also 1 sulfur atom in the seat, or in the particle, or in the molecule, if you want to call it that. And of course, in 1 mole of this, you've got, well, 1 sulfur. Okay, so if you look at the periodic table, sulfur has a 32 atomic mass, which I'm rounding. All right, it also has an atomic number of 16. Okay, but we're going to use the mass number, which is their relative atomic mass that we got. And of course, that gives me 32. I add these together, so simple, and I get 78, but the unit is grams per mole. This tells me if I want a certain number of particles that exist as a gas at STP in a box, and there's a certain number that can fit, that's Avogadro's number, we call that a mole of particles, and that's how many grams a mole of particles is. We already explained why we need a mole. Okay, chemistry is about matching particles and knowing how much of one particle we can come up and make good cake by having the right ingredients or the right ratios. Okay, barium nitrate, same idea. I've got a mole of barium nitrate. How many grams is that? Okay, well, we've got 1 barium, right? And 1 mole of barium, you got 1 mole of barium nitrate, you've got 1 mole of barium. You've got 2 moles of nitrogen atoms, and you've got it 2 times 3, it's right, 6 moles of oxygen atoms. So barium is 137, so 1 times 137, I know my 1 times tables is 137, and I got 2 times the atomic mass of nitrogen, which is 14, it's right from your periodic table, that's 28, I know my 2 times table is pretty good too. Then I have 6 times the atomic mass of oxygen, which is 16. I believe that's 96, if you know your 16 timetables. And now we're going to add them together. So what we got is 261 grams per mole. Now, why is that so much heavier? Well, because in a mole of these, quote, particles, and not really particle, if you want to call it a particle, it's so much heavier because some of the individual atoms are really heavy. And again, these numbers that I'm getting here are from the periodic table atomic masses. But if I wanted the same number of sodium sulfide particles as barium nitrate particles, I would need 78 of these guys and 261. I'm able to use my scale to measure how many. That's the pretty powerful thing. So these are all done the same way. I have a key. There's no use of me going through them. So let's take a walk down to this guy. Okay, so now we have percent composition, which is the next skill that we have involved here. Now, of course, let's say I find a white powder. Okay, I'm pausing. And when I find a white powder, I want to know what it is. One way we determine or analyze, this is called analytical chemistry, is we take the compound and we figure it out its percent by mass. Meaning, let's pretend I have a compound that has sodium, nitrogen, and oxygen in it. Okay, and I identify that by independent laboratory techniques. And let's say I put that compound, all right, in a crucible or some kind of experimental analysis method of determining what these guys are made of. Let's say I put it in a crucible. And let's say I'm able to drive off the oxygen. Okay, before I do so, I mass out the entire total, and I get 10 grams. Okay, that's the total. That's what I started with of the entire compound. And let's pretend that I drive off the oxygen by heating, and let's say I chemically drive off the N by heating and adding, let's say, some water and heating again, and that drives off the ammonia, let's say. So let's say I drive off the N and the O analytically, and I'm left with the sodium. Let's say I'm pretty confident in my number, it's just sodium. Drive off the water and anything other impurities, and I weigh this again, and it's 3 grams. That's just the sodium. And we do this all the time, and because we're finding the percent by mass of sodium, the part that we do, or the part that we care about, is the top number. The total is the total mass, and of course you times it by 100 to get a percentage. So 3 divided by 10 times 100, that would mean experimentally my white powder is made of 30% by mass of sodium. Okay, great. Experimentally, I have that. How can I use that to analyze? Well, what I can do is, with pencil and paper, I can find out what sodium nitrate should be. So let's say I find 30% by sodium. That doesn't tell me the chemical formula. It just tells me that, hey, there must be some compounds out there that have a formula mass, or they have a chemical formula with the right ratio of sodium to nitrogen to oxygen that come up with a 30%. So how do we come up with the percentage using just the formula? Well, the first thing is, let's write a formula. Sodium is Na plus. Nitrate is, what the heck is that? That's an NO3 minus polyatomic ion, and we get that from table E if you have that. And of course, this whole cluster is -1, this cluster is +1, so it's NaNO3. And that's my chemical formula. Now, using the chemical formula, I want to see in pencil and paper if I come up with 30%. And this is called theoretical. This is assuming no error. This was my experimental value, right? We're trying to see what the white powder is. If it's sodium nitrate, this number will approximate what I get right here. So sodium nitrate, without any impurities, without any errors, should come up with a certain percentage. And here's how I do it. Let's assume 1 mole. Why? Well, if I'm finding a percentage, I can assume any size quantity. A percentage is not locked in by a certain amount. It's just a fraction, as you can see here. So by assuming 1 mole, I can do something very important. And if you haven't figured it out, I can figure out the grams per 1 mole. I can figure out the total. So let's go do that. I have 1 Na, 1 mole of Na per one of these, right? So 1 times 23, that's the atomic mass of sodium, is 23. I have 1 N, 1 nitrogen atom. 1 times the atomic mass of nitrogen is 14. I know my 1 times table is pretty good, so that's 14. And then I have 3 oxygens. 3 times 16, if you know your 16 times tables, is 48. Add these bad boys together, and you get a 5, right? 8 and 4 is 12, 2, 15, right? So this gives me 85 grams per mole. All right, well, my friends, in chemistry, that's my total. Since I'm finding a fraction, essentially, I picked a mole. And 1 mole, there's 85 grams. That's where I got that. Now, the part that I care about is the sodium. And I already know in 1 mole of sodium, there's 23 grams. So I plug that in. Very, very, very difficult. And we put this into our calculator, and we should come up with 27%. Now, I can round any way I'd like, because 23 grams over 85 grams, the units cancel. This is the dimensionless unit. There's no significant figures in a percentage. So we got 27%. By what? 27% of the entire mass of my compound is sodium. And if you notice, that's very comparable with my experiment. So my experiment that I made in my head and talked with you with it, okay, shows that the white powder is probably sodium carbonate. Okay, what if I wanted to see if it was iron oxide? Now, iron oxide is not a white powder, but let's see if I wanted to do the same kind of work with iron oxide. So I have to first come up with the chemical formula. Iron is +2. They're telling me that with the Roman numeral. Oxide is -2 because it's oxide, so it's binary. Oxygen is -2, and obviously you need 1 iron per 1 oxygen. And let's do the same thing. The total is what? 1 Fe. 1 times 56. This is the atomic mass of iron. Okay, I think it's 56. Then I have 1 oxygen. 1 times the atomic mass of oxygen is 16. I think that's 16. Add them together, and what I get is 72 grams per mole. That's my total. All right, part over total times 100. I'm going to assume what? I'm assuming 1 mole. Now, I could assume like 3.5 moles or 100 moles. I can do whatever I like, but it makes more work. If this formula mass comes out per 1 mole, why don't I use it? Take the iron, and the 56 goes here. Part over total times 100, and what we get is 56 divided by 72, and you get 78%. So 78% of the entire mass of the compound is iron. So let's pretend I had 2 white compounds. Let's pretend iron 2 oxide was white. It's not. It's a rusty reddish color. Okay, brownish red, I guess. I'm colorblind. Any case, so if you came up with 30% in your experiment and your two compounds you thought they might be, clearly 78% is not 30%, and it would not be the iron 2 oxide. Okay, so they're all done the same way. Now I want to introduce to you something called hydrates here. All right, for instance, let's write iron 3 chloride hexahydrate. Now hydrates are something we haven't talked about yet, so I want to introduce them here. Iron is +3. Chlorine is -1 individually. Okay, if you crisscross a C, you're going to need what? For every one iron, 3 chlorines. But hexahydrate tells me that there are 6 water molecules that are locked in this crystal structure. And you may say, well, how did that happen? Well, they probably took iron chloride. It probably was dissolved in a solution. And as it evaporated away, most of the water, some water molecules got inside the crystal. Remember, ionic compounds are positive attracting negatives in a three-dimensional pattern. You've got to have that visual, okay? So this is a I don't know what I'm doing here. Let's clean this up. So I got a negative attracting a positive attracting a negative. Certainly this isn't the crystal structure, but you get the idea. Ionic compounds go in 3 dimensions. Now what's going to happen, because these were dissolved and these recrystallized in water, you're going to have some water molecules that are locked in the crystal that are part of the overall structure. I'm going to show them having molecule ion attractions here. But you're going to have some waters that are clinging on. In this case, there are 6 water molecules for every 1 iron ion in this arrangement. So, same problem. Let's go find the percent by mass of water. So what we're going to have to do, party people, is we're going to have to do a formula mass. Let's assume 1 mole. So I have 1 iron, okay, which is 1 times 56, which is 56. I have 3 chlorines, 3 times, let's use 35. 105. Then here's what I would do. You can break up into 12 H's and 6 O's, but I like to keep the waters together because I'm going to use them later, as I'm going to show you. So I have 6 waters. I keep them together. And I know the mass of 1 mole of water is 18. 16 plus 1 plus 1. So 6 times 18. 6 times 18 is 108. And now I add these together. And what I'm going to have is the 269. So 269 grams per mole. And that's my total. All right, so 269. And the part that I'm asking for, percent by mass of water, the part I'm asking for is the water. So that's why I use this number. That's why I keep them together. So hydrate questions, percent by mass, they're always asking about how much water. So keep the waters together so you can just grab that. If you did 12 H's and 6 O's, you'd have to add them up again. So keep them together. Times 100, and let's go find that percentage. 108 divide by 269 times 100, and you get 40.14. 40 works for me, 40%. And what does that mean? 40% of the entire mass of this compound is due to the water that's locked in the crystal called a hydrate. Okay, so in any case, what you should do is you should work on the rest of these problems with the key to make sure that you know how to do them. Okay, not too tough. In fact, I think they're pretty straightforward. Let's have a party. Party's over. I said party over.